All right, welcome to the second part of the ideal gas law notes. The thing you need to remember about the ideal gas law, or PERV is that this is the one you get on the formula sheet. You do not get Boyle's law, you do not get Charles' law, you do not get Gay-Lussac, you do not get the combined gas law. You get PERV. So that means you need to know how to use it flexibly in order to figure out other things that you need. So you can take the ideal gas law and you can actually figure out how to get the combined gas law here, which I'll show you how to do. Without having to remember two formulas. You can also take the ideal gas law and put it in a different format that looks like this, which allows you to calculate molar mass or density. Two things that are actually really important with gases, and it's one way that they can have you incorporate a gas problem as part of a larger stoichiometry problem, because we don't typically have standalone gas questions on the free response questions. They're normally subportions of other questions, and this is by far the most common way that they are going to do that. The other way that they do that is in the next section, 8.3, with partial pressures, which we'll talk about then. So I need to show you how to derive these two formulas from the ideal gas law. So we'll do the easy one first. So you can get the combined gas law by stacking you can get the combined gas law by stacking the ideal gas law on top of itself. So this is when you need to deal with changing conditions, right? Because again, the ideal gas law does not deal with changing conditions, only the combined does. So we're going to stack PERV on top of itself. So the first thing you'll do is literally write PV equals nRT on top of PV equals nRT. And then everything in the numerator, we're going to assign as condition 1, right? So P1, V1, N1, R1, T1. And these are typically what we think of as our initial conditions. And then anything in the denominator, we're going to assign a 2, right? So P2, V2, N2, R2, T2. And these are our final conditions. So you do that from the outset. And then the next thing you do is you're going to cancel out stuff. So R is a constant, so it always cancels out, like it doesn't exist. It's not in the combined gas law. But anything else that's mentioned in the problem as constant, or that is mentioned that it didn't change, like it's only given one value, or more importantly is not mentioned at all, you're going to cancel those things out as well. And then whatever you end up with, you're going to have some variety of the combined gas law left. So let's go back to the problem from the combined gas law video before and redo the problem in this method. So again, a gas in a 325 milliliter can, so that's a volume, at 445 kilopascals, that's a pressure, 12 degrees Celsius, that's a temperature, moved to a 101 kilopascal, that's a pressure, and 21 degree Celsius environment, that's a temperature. What's the new volume? Okay, so I've got a V1, a P1, a T1, a P2, a T2, a V2. So if I am looking at my formula up here in red, I have V's, I have P's, I have T's. Moles are not mentioned, right? So no mention of moles. So in my formula, I'm going to cancel that out. I don't have it. So I can rewrite what I've got here as P1V1 over P2V2 equals T1 over T2. And which of these variables is the question asking me to find? Well, it's asking me to find V2. So I need to isolate that. So I'm going to cross multiply. I'm going to get that guy over here. I'm going to get this guy over here, right? So my V2 now is going to be equal to P1 V1 over P2, because none of that changes, and I just need to deal with these things. So my T2 was in the denominator. I'm going to bump it over into the numerator. My T1 was in the numerator. I'm going to drop it down into the denominator. And remember, your temperatures are always with the opposite number. So my T2 is with P1s. My T1 is with P2s. And lo and behold, that's the combined gas law. But I got it from Pervnert. So plugging in all of those numbers, I would get the exact same answer. Okay, so the other form that you're going to have to do is much more common than figuring out the combined gas law. And it has to do with molar masses. So the AP test on free response questions loves giving you problems where you don't know the identity of a substance. And one of the things you can use to be helpful is to figure out the molar mass. But you have no idea how to calculate the molar mass without the formula. In fact, that's the only way you know how to calculate the molar mass. But there are other ways to do it. And one of them is using a derivation of the ideal gas law. So we're basically going to use a flexible notion of what molar mass is, recognizing that it is mass divided by mole. So let me write that over here. Molar mass, and I'm using those M's there, so italicized N's. Molar mass is equal to a mass amount, right, M, divided by a mole amount, N. Okay, so that's my mass, and that's my mole. Okay, and then the other thing we're going to use is density. And remembering that density is mass and volume, so density here is M over V, right? So mass and volume. Then we can use those with our ideal gas law and combine it all together. So my ideal gas law, PV equals nRT. Well, I should notice that I've got an N and a V, and they are connected by a mass, okay? So here's what I can do. If I plug in both of the molar mass and the density, if I basically sub in for that M, right? So mass over here is equal to D times V, and I sub that guy in over here, and then molar mass, woohoo, molar mass is equal to D times V over N. Well, now I've got something that I can actually work with a little bit. So basically, I can plug these things in, and I can rearrange my formula, and I can get pressure times the molar mass is going to give me density times the gas constant times the temperature. So it's a little easier if I show you the reverse of it. So if I plug in P molar mass as M over N and D as being M over V times RT, and then I basically just move these guys, bloop, bloop, and recognize that these guys cancel, then it's PV equals nRT. It's the exact same thing. So that's what I've done. So this formula is known as two different ways. So sometimes we say it's PEMDIRT, because PMM and dirt, PEMDIRT. That's actually how I was raised, knowing this formula. But the other way you'll hear it referred to is the molar mass kitty, because all good cats put dirt over their pee, right? So you've got dirt over your pee, and that's the formula. Molar mass equals dirt over pee, or density, R value, temperature over pressure. Take it however you want. Okay. So in application, this is a common type of formula. It says a diatomic gas, right? Remember that means it's got a something and a subscript of 2, has a density of 1.95 G/L, or that's a mass and a volume, all right? So that's my density at 1.50 atm, that's a pressure, and 27 degrees Celsius, that's a temperature. Determine the molar mass, all right? So that's my molar mass of this gas, and identify it. Okay, so there is no change in conditions here. I only have one of everything. I don't have two of anything. So I'm looking for the molar mass, so I can just use my molar mass kitty, right? Molar mass equals dirt over P. And I know that I need to adjust my temperature, right? So my temperature is going to be that 27 degrees Celsius plus 273, which is going to give me a very lovely 300 point Kelvin. So I've got 3 sig figs there. So if I plug all these things in, open parentheses, 1.95 G over L. An R value, I need the R value that has ATM, and that's going to be my 0.08206 times my temperature, which I just found is 300 K, close parentheses, all divided by my pressure, 1.50 atm. I'm looking at all of this. I've got 1, 2, 3, 1, 2, 3, 1, 2, 3. So I'm going to have 3 sig figs, right? So if I calculate all of that, I'm going to come up with 32.0 grams per mole, because remember, grams per mole is the correct unit for molar mass. So I've done the first part. I got the molar mass of my gas, but now it's asked me to identify it. And they gave me one piece of information that's going to help. They said it's a diatomic gas. And remember, those are only H2, N2, O2, F2, Cl2, Br2, and I2. So I can automatically say, well, it's not hydrogen because that would be too small, and it's not iodine or bromine because each one of those is individually larger than that. So nitrogen has an individual mass of 14, so a diatomic mass of 28. Oxygen has an individual mass of 16, so a diatomic mass of 32. Fluorine has an individual of 19, so a diatomic of 38, etc. So the answer has to be oxygen. So my diatomic unknown gas here is oxygen. And that's how you're going to use PervNert along with a density value and molar mass. Now, if they did not give you a density, if they didn't give you density, the thing to look for is a mass and volume somewhere in the problem. Because if they give you a mass and a volume, then they did give you density. So you can also imagine that this formula is M over V RT P. That's the same thing, just flexibly thinking that density is M over V, okay?